Today, we're talking about Lewis structure and line angle structure. Both of these are used widely in organic chemistry. However, line angle structure is used a lot more since Lewis structure can get out of hand. So I want to start off with some relatively simple stuff, and then I'll ask you a couple questions, and then I'll explain those questions. So, to start off with, we have ethanol. Ethanol, CH3, CH2, OH. Okay, so here we have it in the Lewis formula. We have a carbon, sp3 hybridization, we have all the bonds. It's a happy carbon, CH3, and then we have all the bonds here, another CH2, then we have our OH group. And remember from the first video of functional groups, you want to still label the happy oxygens you can. The little smiley face, well, it's not that happy, but put that smiley face in there. That is happy, and then you can add the extra bond if you want there. But usually it's just the OH, as we know. And as everyone knows, an OH group, it's A, keeps the stress away. But that's our ethanol. So, then we go to line angle structure. Line angle structure doesn't usually express much. Kind of boring, like, just like a line, it's boring. It's not all BAM! But with simple stuff, this is okay, but for this it's okay too, but when we get to bigger problems, like I'm gonna bring up soon, you'll see the difference. So here we are. We have two carbons. I'll point them out if you cannot tell. So, here's our first, and here's our second. And line angle, where it starts and where something finishes, represents a carbon, a hydrocarbon. And then if there's an O, let's say the branch connects to the O, then it connects, and it's an oxygen. It's a hydrocarbon and an oxygen. So that is ethanol. CH3, CH2OH. They both are written out the same way. Your professor says draw ethanol. Which way? There you go. That's how you can do both ways. Okay. So that's ethanol. So that's pretty simple, straightforward. Now let's move on to cyclohexane. Cyclohexane. It's used a lot. It's well known. All the cyclohexane is used more than cyclooctane or cyclopentane, for that matter. Ooh, drawing the wrong side. So used to drawing line angle structures. Not the best, but that's line angle structure of cyclohexane. Pretty simple. Looks like something from geometry class. So yeah, here's cyclohexane, drawn as a Lewis structure. Oh geez, I'm messing up. So there we have it. 6 carbons. Carbon 1, 2, 3, 4, 5, 6. They're still all sp3 hybridized. When we get to double bonds, that's a different story. So, let's add on our hydrogens. See, with Lewis structures, you just can't tack on groups. So say, after I'm done this, I throw in a methyl group. Lewis structures tend to take a while too. That's why line angle structures are used a lot more than Lewis structures. So we have to draw out all this, and here we are. All the bonds are met, all the requirements are fulfilled, and there's cyclohexane. Here's cyclohexane for line angle structure. Very simple. Look at it, just pop. This, there's a lot to it. That's just basics. This is just basics. Alright, so next order of business is let's get into double bonds and triple bonds. So we're going to use cyclohexene, or we can use benzene. You know, let's use benzene because that's used more. Alright, so let's throw in a benzene. Benzene can be drawn various ways too. This will end up leading up to chair formations, probably in the next couple of videos. There we are, making the mistake again. So used to drawing line angle structure. So, benzene has its own name. Double bonds. Here, here, and here. You can also draw it. If you're going to take a guess before I show you, go ahead. You're right, with a circle. That's another way of seeing benzene. Pretty interesting. So, those are two ways on the line angle structure. Now with the Lewis structure, we're going to draw our carbons. And sometimes it's easier to draw it out this way. I'm going to erase the names over here. Okay. Now look. 6 carbons. Look at these double bonds here. sp2 hybridization. So that means only one hydrogen can latch on, so it's always 4. People always can make the mistake to throw on 2 and then it defies the octet rule. But remember, with the benzene ring it's always 1 hydrogen all the way around. And you'll see when we start throwing on R groups and everything like that, it gets a little fun. Changes up quite a few things, should I say. Alright, so let's throw in some practice problems. You know the rules, hopefully from class, and you also should know the basic things I just showed you. So I'm going to draw a molecule and give you guys a second to choose what it is. Okay, I'm going to draw it in line angle structure. Alright, so here we are. You're going to pause your video for a minute before I get started. These are the two. Right here and right here. Alright, so I'll begin. So here we are. I'll give you the names. So we have 1,1 dimethyl methoxy. I'm running out of room. Ethane. Okay? No, I'll come to this one later. But okay, so we have 1,1 dimethyl methoxy ethane. I'm going to put a little dash here. That is, can somebody tell me what type of name that is? You're right, it is, my fantastic markers always help out. An IUPAC name. Alright, so why is it called methoxy? Whenever there's an ether present, it's an oxy. Methoxy. There's one ether. And then you can obviously decipher the rest. Dimethyl. So here's a methyl group, here's another methyl group over here. And then we have an ethane. Right there. Right in there. And you might think, oh, this looks a little confusing at first. Heck, it looked confusing for me when I first saw it. That's why, if you want to use a common name, it makes it a little easier. And common names don't have any regulations. So here's an example of a common name. Methyl tert ether. Methyl tert ether. Methyl group, tertiary group, and then there's the ether. No regulation, no IUPAC specification. So yeah, it's a lot easier. Alright, so let's draw it in a Lewis structure. So remember, carbon bonded here to our oxygen, bonded here to another carbon, another carbon, another carbon, another carbon, and let's fill out everything here. So here's our hydrocarbon CH3, here's our oxygen, here's another carbon, and it's a tertiary. Here we are. 1, 2, 3. Looks like the finger prong coming at you. Adding all these hydrogens can be a pain. And there we go. Fills all the octet rule, and that's our molecule. CH3. You know we can make it, yeah, OCCH3. Oh, forgot a hydrogen. CH3, 3. Okay, so that's that. That's that one example. I'll be quicker on the other one. And at the end, I'm going to go over a couple quick branches, and then we will be done for this session. Actually, you know what? I'll get that one. I'll just post up later. I'm just going to go over some practice branches, because that's very important. Get down. Don't mind the certain lengths, just putting them out there. So, our objective here is to find the longest chain, which is very essential in deciphering this molecule because without the longest carbon chain, you can't even make that is the backbone of the molecule. So let's use a different color and specify where our longest chain is. Okay, so we have 1, 2, 3, 4. Okay, well obviously we're not continuing here, but there's obviously more right here. So we want to keep that because that's a group. That's a methyl group. Here we go to 5. Up we have a ethyl group right there. And then 6, 7, 8, 9. We have 9. But can someone tell me, is there anything wrong with this? Say if we counted it backwards. 1, 2, 3, 4, 5, 6. No, there's no difference because they're equal length on both sides. Now say if this was longer, this chain was longer, then we would count from this side first, like I originally did. And then you would, because like I said, IUPAC wants the lowest numbers. Always the lowest numbers, never the highest numbers. Marker down. So let's name this. Let's find out how many there are. There's 9 in the longest, so that's known. Single bonds, ane, known ane. That's our backbone of the molecule. So where do we have our methyl and our ethyl branch? Well, you're going to look here. We have a methyl group at the 4. So we're going to put 4-methyl. Oh, and then we have an ethyl group at the 5. So, add that on there. So 5-ethyl no nane. Relatively simple. This is like your guide to drawing out the molecule. After you write this name out right here, you should be able to draw this exact replica. It might be another way around, but as long as the groups are present, it's still the same molecule. Alright, so let's do some double bonds. Alright, so let's do something simple like a chain. So let's do butane, right? 1, 2, 3, 4. As you can tell, I'm sure in chemistry or organic chemistry, you'll start seeing the trans and the cis isomers and everything coming up soon. So here we are with an alkene. Remember what I said about alkene, double bond. Alkene. E-N-E is the key word in that. So we have not butane, but butene. 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 So let's count the carbons. 1, 2, 3, 4. So since this is a butane, we don't have to be selective where the double bond is. Now if the double bond was over here, we'd hit that right off the bat. But instead, either way it's 2. 1, 2, 1, 2. So it doesn't matter which way you count. So we just know it's on the 2. Now remember what I said, that's old IUPAC. If you want to write the new, be my guest. And there we have it. 2-butene. That's it. Pretty simple. Self-explanatory. Now, let's go to that one molecule I was talking about earlier.